Yogah Karmasu Kaushalam.
I am Rusvi Gandhi from Department of Chemistry, Gujarat University. I welcome you all in today's session of Dr. Ranjan Khunt, Assistant Professor, Department of Chemistry, Saurashtra University, Rajkot. She has completed her graduation, post-graduation and doctorate degree from Saurashtra University. She has completed Diploma Patent Law from National Law University in 2009. She has cleared GSET in 2013 and Basic Computer Programs from SPIPA in 2013. Her research area includes heterocyclic chemistry, medicinal chemistry, nanoscience, NMR, and method validation. Dr. Khunt has 16 years of teaching experience as an assistant professor in Saurashtra University. She has 3 years of research experience as a principal in a Young Scientist Project, DST, New Delhi. She has guided 6 research scholars as a PhD and MPhil during her tenure till date. She is having professional membership as exclusive member in a Nuclear Magnetic Resonance Society, Mumbai. She has 2 patents as a part of research credit and completed 2 research projects. And presently 3 research projects are ongoing. She has attended and presented a paper in 10 national and 13 international conferences. She has attended 19 workshops, seminars and conferences. She has 14 national and 34 international publications and 6 books published. Thank you very much.
Myself, Dr. Ranjan Khunt from the Saurashtra University Chemistry Department. So in today's lecture, we discuss regarding the small molecules and Nmr spectroscopy. So let us discuss here how Nmr spectroscopy will help us for that things. So we start with the spectroscopy. What do you mean by spectroscopy? How it will be help us? So I will start from the very basic of this. Very basic of the NMR. So we can see that Nmr spectroscopy is a unique tool. Why it is known as a unique tool? We can see that it has application in the different branch of science and technology. In this slide, it is applicable to agriculture. It is also applicable in medicine as a MRI, one of the good tools for the diagnosis of the disease. And our main focus on how it is helpful in chemistry. So we start think about that things for that, and further it is supported why it is unique tool. So here we can say that Nmr spectroscopy is applicable for a various field. Several Nobel Prizes have been awarded in the field of NMR by in a different branch of the science. So from very beginning, Felix Bloch awarded a Nobel Prize in 1952 for the development of nuclear magnetic resonance or induction. How it can be help us. And later one is further awarded, Nobel Prize is awarded on R.R. Einstein in chemistry to find out high resolution NMR methods for that things. Further, it is also awarded in chemistry in 2002. K. Whitman find out for the 2D Nmr spectroscopy for the protein molecules, and last it is also awarded in medicine for the development of a MRI as an image and for the diagnosis of that things. So it can be applicable in a various field of science and technology. That's why we can say that it is nothing but the unique tool related to it is a unique tool of spectroscopy. Before, let us go through the basic concept of spectroscopy before we proceed for the Nmr spectroscopy. So what is spectroscopy? So here you can see the pictures. What do you mean by this picture? So we can see that it can be represent 2 colors. One is blue color, another one is the red color. Meaning of that thing, spectroscopy involves the study of interaction of radiation with matter. Now this radiation is nothing but the electromagnetic radiation, and that electromagnetic radiation is a mixture of 2 compounds. One is electrical component, another one is a magnetic compound. So this blue color is a representation of the magnetic component and red color is the representation of the electrical component. Now in this picture we can say these two are perpendicular to each other, means electrical component and magnetical component are perpendicular to each other. And when we see this is nothing but the propagation line or direction line. So these both are also perpendicular to the direction lines. Now this type of radiation when interact with this matter, so this matter may be a molecules, it may be a and subject or anything, it may be human body parts also. So when they interact with this matter, it will give the some results, and this result, why? Because these waves will provide the energy. Now the question is that where the energy will be, in which region energy will be provided. So here we can say this is energy. Energy is nothing but the H into V, where V is nu is nothing but the frequency of the waves and H is Planck constant. So from that we can say that how it can be interact with this. So spectroscopy, it's nothing but only the one technique, but it is also depends on the different parts of the frequency, or we can say that where it can be absorbable. Depending on the property which want to study the, for example, here you can see this is the infrared region, this is the microwave region. So infrared radiation, it is nothing but we can say it is related to the direction and vibrational and rotational related to. So in that region when we provide or pulse the radiation on a molecules or a matter, then that type of physical phenomena occurs in molecules, and according to that things we can get the information by the study of that where the absorption will be takes place and what is the reason for that. So according to that we can get the result related to that thing. So when they absorb infrared region or microwave, then molecule physical phenomena occurs, it is rotational and vibrational related to that thing. So at that type of phenomena occurs in physical changes occurs in a molecule or matter, and as per that things we can get the radiation related to that things, result we can get related to that thing. So that we can consider here this the spectroscopy. So spectroscopy also depends on the wavelength. Now we start from the wavelength from lower and short wavelength to long wavelength, or we start from the higher frequency to the slower frequency. So what is the relation between frequency and wavelength when we consider like that thing? So if the frequency is very short, wavelength is very short. Frequency is very high, wavelength is very short, means it is highly energized. Means relation between energy and frequency, it is parallel to each other, while wavelength relation between energy and wavelength, it is inversely proportional to that thing. So in gamma rays the frequency is 10 raised to the power minus 12, means it is atomic nuclei. It can be physical phenomena occurs in that, it is just like a atomic nuclei related to phenomena. Then X-ray, then ultraviolet, visible, infrared, microwave, radio. So here is the highest wavelength, here is the shortest wavelength, here is the highest energy, here is the lowest energy. So from that we can say that which type of phenomena is occurs and what is the spectroscopy. So in case of NMR we study related to this radio frequency. So it is harmful as compared to the other things, it is harmful for us or human body. And cosmic rays or gamma rays, when we see that, then it is very hazardous for the human body or any animals present on a earth. So from that this is also known as electromagnetic spectroscopy, EMR spectroscopy, and from which part will be absorbed and which type of frequency falls on the molecules, according to that the result will get. So this is the some brief review related to the spectroscopy. Now we move towards the NMR spectroscopy. So we start from the very basic of the NMR spectroscopy. What is NMR spectroscopy? So in this slide, in this picture, especially we can say that in this slide, especially we see in that picture. So in this picture we say that here what is called matter. This is matter. What is called matter or sample or molecules is made up from atoms. Generally it is made up from, as per basic chemistry or physics, we can say it is made up from atoms. Now atoms is made up from electron, proton and neutron. Now neutron and proton present in a nucleus, and nucleus is nothing but the center of atom. So electron possesses one spin, as it is proton and neutron is also possess the spin. So when it possesses the spin, the difference between neutron and proton. So if we say that they have a property difference in proton and neutron. Proton possess spin, also neutron possess spin. But proton possess some charge, neutron does not possess some charge. Now this spin when deposited on the center of this nucleus, so overall nuclei charge will be spinning will be occurs, nuclei spinning will be occurs, and it purges positive, overall charge is positively charged. So this type of nuclei is known as spinning nuclei. This type of nuclei will known as spinning nuclei. And here we can say the net spin of the nucleus is equal to the sum total spin of nucleons after pairing of them up. Nucleon spins proton and neutron. So total spin of the neutron and proton is known as net spin of the nucleus, and it is sum of nucleon spins. The net spin can be 0, half, or integer, or half integer or an integer. So we see that how it is 0 spin, how it is integer spin, and how it is half integers. So many elements in the periodic tables have non-zero nuclear spin. If they have a non-zero nuclear spin, these are elements or isotopes are called NMR actives. These elements or isotope calls NMR active, means which type of elements absorb the NMR or give the result. So if non-zero nuclear spin types of atoms, molecules, elements or isotopes give the NMR active. Any molecule containing such element is amenable to study for the NMR spectroscopy. If they are NMR active, means we can study this nuclei under the title of NMR spectroscopy. Now we start, we think about when it is 0, when it is half integer, or when it is full integer. So here you can see that we divided this periodic table in a 2 class on the basis of their mass number. If mass number is even, then atomic number is even and odd. If mass number is odd, then further we classified that is atomic number is even and atomic number is odd. So when it is possible. Now first we clear one thing, that what is atomic mass? Atomic mass is nothing but the summation of proton and neutron. It is nothing but the summation of proton and neutron. So in that case, if atomic mass is even and atomic number is also even, atomic mass is even and atomic number is also even, so at that time the spin quantum I is equal to 0, means it purges the spin 0. So when it purges spin 0, then it can be NMR inactive. So which type of molecule? For example, first case we discussed related to that things. So that is nothing but the carbon 12. Now in case of carbon 12, 6 proton and 6 neutrons. After the Boltzmann distribution, population is half. So at excited state, in case of proton 3 and then ground state proton 3. Same thing, neutron 3 and neutron 3 at excited state. But proton spin cancel out by proton and neutron spin cancel out by neutron. So there is no population difference after cancel outing the spin. It means I is equal to 0. Same thing for the oxygen. So in case of oxygen, 8 protons and 8 neutrons are there. So if it is 8 protons and 8 neutrons are there, population as per Boltzmann distribution, population is 4 neutron and 4 proton at excited state, 4 proton and 4 neutron in ground state. So proton cancel out by proton, neutron cancel out by neutron. So there is a further, it is no population difference. It means I is equal to 0. If I is equal to 0, then it is considered as a NMR inactive. Now in the second case, if atomic mass is even and atomic number is odd. Atomic number is odd, it means what? We can say that either proton odd or neutron odd. Both are odd. Proton and neutron both are odd. So summation is even. So atomic mass is nothing but we can say the summation of proton and neutron. But here it is odd. So number of proton is odd and number of neutron is odd. So after Boltzmann distribution, some of the nuclei, it is proton and neutron. They are either in excited state or in a ground state. They make a population difference, and as a result population difference, what is that? There is a I is equal to not 0. If I is equal to not 0, then means it is I is equal to half integral. I is equal to half integral. Now third case related to that, atomic mass is odd. So when the atomic mass is odd and atomic number is even, here in case of odd and even, out of these two, one may be odd, one may be even. Now in case of odd means both are odd. Both are odd means number of proton and number of neutron are odd. So at that time atomic number is even. So atomic number is even. So I is equal to 1 by 2, 3 by 2 or 5 by 2. So here we take the example of C13, which is nothing but the isotope of C12. It possesses one more neutron it possesses one more neutron, and which make a difference in population distribution. So this difference is represented as a spin quantum number I. So it is I is equal to 1/2. Same thing for oxygen. So oxygen, it make a difference, and it is I is equal to 5/2. And if we take the chlorine 35, then it is 3/2. I is equal to 3/2. Now fourth case is half integral. Fourth case is half integral means we take itself hydrogen. Hydrogen only possesses one proton. There is no neutron. So when we carry out the summation of spin of neutron and proton, only proton is there. So it is 1/2. In case of nitrogen, 7 protons and 8 neutrons. 7 protons and 8 neutrons. So 7 protons means there is a difference, and 8 neutrons there is no difference. So due to that, it possesses 1/2 spin related to that. It is an isotope of 14N. It is an isotope of 14N. So we can do that related to that things. So this principle we can extend it here in all over the periodic table. No doubt this is not enough information for the for getting the information whether it is NMR active or NMR inactive. But from that we find out that whether atomic mass is odd, even, and mass number is also even or odd. And from that we can say we find out some non spin zero molecules and atoms, sorry, and that atom is responsible to give the spectrum. So it may be an atom or it may be their isotope which are NMR active. So from these last two slides we can say which type of molecule can give the NMR spectrum and which type of molecules cannot give the NMR spectrum. Now what is NMR spectroscopy? So NMR spectroscopy, if we say that it is nothing but the nuclear magnetic resonance spectroscopy, it is basically another form of absorption spectroscopy. Nuclear magnetic resonance means NMR spectroscopy is basically another form of absorption spectroscopy. So we can say that here we use the word resonance. So where the resonance will be takes place. Generally we can say resonance will be take place for the stabilization. Resonance will be takes place for the stabilization. So here some type of stabilizer, which type of stabilization? Maybe it is spin stabilization will be takes place here, and that's why it is known as NMR magnetic resonance spectroscopy. So in which form resonance will be takes place? So here it is magnetic field. So we can say the resonance will be takes place between two different magnetic field, and between two resonance will be takes place. So it is nuclear magnetic resonance. Why? Because nuclear will be responsible for this magnetic field, and other one is the external magnetic field. So resonance will be takes place between the induced magnetic field and external magnetic field, and by applying the waves. So when we apply the waves, then it is known as spectroscopy. Interaction will be takes place, and that's why it is known as nuclear magnetic resonance spectroscopy. And it's basically another form of absorption, means one type of absorption will be takes place. Here emission will not be takes place, but some frequency will be absorbed by the molecules as a function of certain nuclei. That's why it is known as absorption spectroscopy. Under appropriate condition in a magnetic field, a molecule can absorb the radio frequency. Absorption is a function of certain nuclei in molecule. Now, plot of the frequency of the absorption peaks versus intensity is continuous to NMR spectroscopy. So, as we discussed in 6th slide, proton and neutron possess some spin, and proton possess charge which is deposited in imaginary axis of the nuclei, and overall charge is positive on a nucleus. So nucleus also possesses spin, and due to this it behave like a bar magnet. Now how it can be work as a bar magnet we can discuss in the next slide, but these are the some things it is important, and that's why we can get the NMR signals. So one important parameter, it is spin quantum number. Second one is spinning of the nuclei. So now this whole nuclei can possess spinning. Why? Because deposited of the charge on a center or imaginary axis. But this due to this spinning, it induce some magnetic fields. Means it behave like a bar magnet. It behave like a bar magnet. So in absence of external magnetic fields, they are random in phase. In absence of external magnetic fields, they are random in phase. But when we insert this type of sample which possesses the nuclear spin into the magnet, means in presence of external magnetic field, they will try to adjust their spin according to the direction of the applied magnetic field. So some are parallel, some are anti-parallel to the applied direction of the applied magnetic field. So these things we can clear here that what is that. So first, due to spinning, it will possess magnetic behavior. and magnetic behavior, but they are in absence of external magnetic field. They are random in fashion. When we apply for the external magnetic field, try to adjust their position. So you can see here that things. Now, in those conditions, if we irradiate with the waves, and particularly in case of nuclear magnetic radiation, we can say it is radio frequency. So when we apply that things, according to the Boltzmann distribution, splitting of the energy level will be takes place. When it is takes place, it will convert into the different energy levels, excited level and ground state. Now, how much excited level, how much ground splitting will be takes place, it depends on the gyromagnetic ratio of the atoms. So we discuss later on, and differences also depends on that things. So here only we can say that distribution will be takes place by absorbing the radio frequency waves. Now how much? So for example, suppose we study the 1H NMR. So in case of 1H NMR, 1H NMR I is equal to 1. So we put this value 2I plus, put this value in 2I plus 1. So 2 into 1 plus 1. So 1 plus 1, 2. So energy difference here, we can say that it will energy level will distribute in two levels, plus 1 and minus 1. For chlorine, it is 3 by 2. For chlorine, it is 3 by 2. So it is 2 to cancel, 3 plus 1, 4. So here we can get plus 1 plus 3 by 2. Sorry, plus 3 by 2, plus 1 minus 1 and minus 3 by 2. So according to that, it will be takes place. And this is calculate on that. So what is energy? So energy is nothing but the mu into B. Mu is nothing but the magnetic momentum, and B is the strength of applied magnetic field. Now what is mu? So mu is nothing but the 2h eta I upon 2 pi. H is the Planck constant. Eta is nothing but we can say that gyromagnetic ratio for the particular nuclei. I is nothing but the spin quantum number, and 2 pi. Why? Because it is spinning. So spinning will take place at 360 degrees Celsius. So that's why we use that things. Further we discuss these things in a next slides. What is this next slide? So here you can see that just in a spinning nuclei will be rotated, and that is the vector. Vector is magnetic vector, and this magnetic vector is nothing but on a z axis. So it is just like that. So under the effect of gravitational force, they will try to adjust their position. And what happens? So they slightly deviate from their original axis. If they slightly deviate from original axis, so that is known as angular momentum. And that frequency is known as precise frequency. That is Larmor frequency or precise frequency. So that precise frequency, you can just compare this spinning nuclei with the spinning gyroscope and in the gravitational fold. So you see that here. Now in this condition, what happens? So external applied magnetic field, it is on that direction, and vector will come onto the z axis. So you apply the radio frequency for that things. It absorbs the energy. So that radio frequency is nothing but on the y axis. Means all three are perpendicular to each other. Now magnetic moment mu is associated with a spinning spherical charge will precise in presence of external magnetic field, and spinning nucleus has been placed at the origin of Cartesian coordinate system is x, y, z. So you can see here how it will be takes place, and what happens when we put under the external magnetic field and after application of the radio frequency waves. So in next slide we see that how the magnetic moment mu associated with the spinning spherical charges and will precise in external magnetic field. So this equation will show the relation related to the gyromagnetic ratio, angular momentum and the magnetic momentum. So here you can say the mu is nothing but the eta into p. Mu is nothing but the eta into p. So what is eta? Mu is magnetic moment of the spinning nuclei, which is due to this spinning charge of a spherical charge of a nuclei. P is the angular momentum. When we put under the external magnetic field, it will slightly deviate. And what is the deviation? That is known as angular momentum. And eta is the magnetic ratio. And it is particularly for the difference constant for the particular or certain nuclei. What is angular momentum? So angular momentum P can also be represented as a omega. So omega is nothing but the minus eta into B0. B0 is nothing but the strength of applied magnetic field. Now what is delta E? We have already seen that. So delta E is difference of the energy. Delta E is nothing but the h into omega. Omega is angular momentum. Now put the value of omega. for 360 degrees. So if we put the value of for 360 degree h into eta b0 upon 2 pi. Now where s is Planck constant and I means spin quantum number, I x is equal to ks ns. Ks is the NMR spectrum constant and n is the number of nuclei. So from that we can find out the how much energy difference will be takes place by using 2i plus 1 equation. How many splitting level will be possible in case of this in case of when we apply the radio frequency or study of the NMR spectrum. Now what happens? So some parameters are very important. Let us show how actual experiment recorded in NMR data. Means what happens, what is the step and what are the some parameters is important for the recorded the NMR spectrum. So we can say that every NMR, first we just discuss this regarding the pulse sequences. What do you mean by the pulse sequences? If we know number of spectrophotometer is available commercially with default pulse sequences, but if we don't know about what is the function of pulse sequences, what is the importance of pulse frequencies, so due to the some changes in pulse sequences, some results may be created default, means we cannot get the exact result, but some mistake will be happen. So if when we carry out the interpretation of the spectrum, we cannot find out the exact result. So if we know regarding the why this will be occurs, what is the mistake done by the operator, so we can discuss with this operator. So that's why it is necessary to know some this. So pulse sequences is nothing but we can say it's a bunch of radio frequency. It is a bunch of radio frequency. Why? Because here in case of NMR study we use the radio frequency. That's why I say that it's a bunch of radio frequency. So in every NMR equipment has associated with the pulse sequences. Pulse sequences consist of a series of radio frequency pulses precede or followed by period where number of RF pulse is applied. This period is called the delay, which is also known as preparation delay. And why it is necessary, we discuss later on. The delay and RF pulses applied are appropriate for the given experiment. Means value of delay in a microsecond or a millisecond it is also fixed and the RF pulses is also fixed. So the delay and RF pulse are applied appropriately for the given experiment. During the final delay in the pulse sequences, the signal is acquired in the form of FID. Means it is in the form of time dominant spectrum. It is not a frequency dominant spectrum, it's a time dominant spectrum, means how much time it is absorbed by the matter. So that is known as FID. Now pulse sequences is like a blueprint of NMR experiment and every details of the NMR experiment is embedded in the pulse sequences. Means pulse sequences is very much important for that thing. Generally what happens, so we can say that it is applied at 90 degrees Celsius. Why we apply the 90 degrees Celsius? Because we consider that in external magnetic field we applied that is on one direction, another direction is the nothing but the induced magnetic field produced by the molecules due to the spinning nuclei, and third we apply the radio frequency. So radio frequency we apply in the perpendicular to the both associated magnetic field, external as well as internal magnetic field. So that's why we generally say that we apply the 90 degree pulse. We apply the 90 degree pulse. So generally apply the 90 degree pulse. It is a single pulse. So first time when we apply for that is single pulse. If we use only one frequency, then it is known as single pulse and it is always applied at 90 degree Celsius. So in experiment, nothing but the delay is a very short in a few microseconds. In a delay is nothing but a very short and few microsecond. After final delay, pulse program start recording to the signal which is known as FID. So this is related to this slide. What is pulse sequences? Now in next slide we discuss related to that things how. So this is nothing but the pictorial diagram of the pulse sequences and all experiment done in the NMR recording. So in case of NMR recording, if we done that things, how it's, so when we insert the sample in the magnet, you will have to wait for some times. You will wait for some times and that is called preparation delay or delay. Preparation delay or delay to establish the equilibrium situation. To establish an equilibrium situation. The equilibrium situation, if we give some delay, that is known as preparation delay. After preparation delay, we apply the 90 degrees is a single pulse. So that is nothing but the excitation. That is nothing but the excitation. What happens? So when we give the preparation time, as per the Boltzmann As per the Boltzmann's distribution law, population will be at excited level as well as the ground state level. So in excited level and excited, but when we give the energy at 90-degree pulse, it means it is excited. So redistribution of the pulse will be population will be takes place, and after some times it will come to the ground state. That is known as acquisition or acquired prediction. So after some times it come to the ground state, whatever the population difference will be occurs due after the excitation, that is responsible to give the signal. That is responsible to the signal. So that can be done by the acquisition process and detection of the signal. So this whole experiment will be carried out during the record of the NMR spectrum. Now, what is the pulse sequences of 1D NMR spectrum? What is the relaxation delay and how it? So this is nothing but the preparation delay or relaxation delay, and after that we apply the 90-degree pulse. So we can say that it is a pulse excitation state. After excitation it come to the ground state, which if it is comes to the ground state means population difference will be created and acquisition of the spectrum will be takes place, and we can get signal in the form of FID, pre-induction decay. So this is known as related to the full pulse sequences for 1D NMR spectra as a single pulse. So after that time further we repeat this process, and that is known as number of scan. So if we want to do that things further, we require some delay process. So this is known as T1. But after completion of one scan, we apply for the second scan and we give some delay, that is known as T2. We do later on what is the importance of T1 and what is the importance of T2. Here you can see the picture of 400 MHz Evans 3 with 5 mm BBO multinuclear probe head. Multinuclear probe means you can scan here 1H NMR, you can scan here N15 NMR, you can scan here 17 NMR spectra, you can scan here C13 spectra, but not for the fluorine. Why? Because fluorine have a 3 channel, and in that instrument only 2 channel is there. So we can say no doubt it is a multinuclear, but it is not responsive, not recorded at the fluorine 19 spectrum. Now here you see that this is nothing but the slide. You can see the entire process of acquiring of the NMR spectrum. So first step is nothing but the sample preparation. So means you can take any solvent and prepare a solution, not to undissolved particle. Any undissolved particle make some resistance, so you can test it. Now insert into the magnets and wait for some time, which is known as the preparation delay. Preparation delay is also known as T1. After some time it is necessary for the equilibrium, I mean distribution of the population at different energy levels, and then after equilibrium you apply at 90-degree pulse. So this is nothing but the excitation test. After excitation further it comes to the ground state, redistribution of the further convert into the equilibrium, and due to the population difference after excitation it creates some signals which can be done by the aquarium of the spectra, and that acquisition process whatever signal will be converted into the FID. So this is FID by applying the Fourier transform, means transmittance in that time dominant spectra into the frequency dominant spectra, so we can get this spectra. So this slide will show the total process in a pictorial form, but each and every step has on their importance, work, and why it is necessary. So we start from the sample preparation. What is the importance of sample preparation? Which type of solvent we can use for the sample preparation? If we not use that, what is the requirement volume? How much volume we can take? Which type of tube we can use as a sample tube in case of NMR? So in most of the NMR spectrum, what is called as a 5 mm probe. We have already seen that in instrumental picture that it is 5 mm BB broad. So if it is 5 mm probe, it is sufficient. We take either 500 to, means we can take 500 to 600 microliters suitable solvent for the solvent height in a NMR tube. So we use 500 to 600 microliters suitable solvent in that, and for the solvent we use water. We can use deuterated water, we can use CDCl3, or we can also use DMSO. But relation it to this, particularly in sample we use 500 to 600 to make a level. I mean to say that to provide a homogeneous magnetic waves passes through that sample, it is sufficient for 500 to 600 microliter. The solvent should be contain deuterium nucleus. If we use water, add 2 to 3 drops of water to log the deuterium frequency, and it is necessary for that thing. The solvent should contain deuterium nucleus. Otherwise, in addition to primary solvent, a small amount of D2O can be added. But when it's possible, if D2O is miscible with the primary solvent. If it is not possible, then you cannot use this technique. You can use 100% deuterated solvent. The sample should be completely soluble in the solvent. If some particles are there, so when we pass the magnetic waves, it absorb the waves and reflect it. So it make a hurdle. So homogeneous atmosphere cannot be created by that particle. So sample should be completely soluble in solvent. Any undissolved or floating particles in the solvent will cause the problem with shimming. So shimming is another parameter, and it is also important for recorded the NMR spectrum. Typical concentration, generally we require 1 to 5 millimolar. If the molecule are at 500.3 milligram in 600 microliter, so it is 1 millimolar. So we use this solvent for that things. In next important point is that reference compound, internal reference standard. So what is the internal reference standard? In case of that things, if we use D2O as a solvent or H2O as a solvent, we use the aqueous solution. So tetramethylsilane cannot be used as an internal standard. But if we use CdCl3, DMSO or any other solvent, so at that time we can use TMS as an internal standard. For D2O and H2O, we use DDS. Why? Because salt is soluble in water and it is also soluble in deuterated water. So DDS is salt, sulfonate salt, sodium salt of sulfonic acid, trimethyl pentasulfonic acid, and that's why we can use that things. Otherwise, we cannot use that thing. So this is the things how we can prepare the sample. Next important point for recording the NMR spectra, that is 2 points here we discuss in this slide. One is the insert the sample in magnet. Second one is the locking, shimming and turning. What is the meaning of locking, shimming and turning? We discuss. But first we sample insert. So generally what happens here in right side picture, you can see that we insert the NMR tube. Means we take a compound in a dry NMR tube, add up to 600 ml, 600 microliter solvent, which is maybe a D2 or any deuterated solvent. If it is not deuterated solvent, we add D2O if it is miscible with this primary solvent, and adjust the height with the help of turbine, and then we insert with the help of hydraulic at upper part of the center of the instrument into the net, and it will be goes to the inside the instrument where the magnet will be located. So we add these things. So the solution containing dissolved samples should be put in a clean dry tube. NMR tube is inserted in the magnet and the temperature is set to desired value. Now third point, temperature is set to desired values. Generally we carry out this practical and recorded the data at 25 degrees Celsius. But sometimes if temperature is higher, then NMR spectrophotometer cannot work properly. So at that time what we do? We try to adjust the temperature by temperature. Generally the temperature should be set by applying the airflow. So we keep refrigerator near to the spectrophotometer and apply the airflow by providing 15 to 20 degrees Celsius. So it will convert into the 20 degrees Celsius. So temperature is set to desired value. And next point is locking, shimming and tuning. So what is locking, what is shimming and what is tuning? So locking is nothing but adjust the frequency according to the deuterium atoms. Why? Because we use the deuterated solvent or deuterium. So to lock this signal, otherwise whole screen can be spread out by the solvent signal. So it is necessary. So we log this deuterium frequency by this thing. And then shimming. Shimming means to provide the homogeneous atmosphere. Homogeneous magnetic waves passes through that. So what we do? So we spin the tube. We spin the tube, sample tube, by using the airflow only insert by in a turbine. So this shimming. So the purpose of shimming is nothing but we can say that provide the homogeneous magnetic atmosphere to the sample. And last one is tuning. Tuning means adjust the frequency. If we study for the 1H NMR, then we can say that adjust the frequency by turn the radio frequency knob related to the 1H frequency. So this is known as tuning. So in that second point, first point is sample preparation in appropriate solvent. Second important point is nothing but we can say that by insertion of the sample and set the desired temperature. Third important point is locking according to the deuterium molecules. Fourth, the shimming. Fifth one is the tuning. And after this tuning, what happens? After this tuning, just we apply for this. So it is necessary to source the signal in the given range. So that can be done by setting the carrier frequency. That can be done by the setting the carrier frequency. So what do you mean the setting the carrier frequency? Typically small molecule can zone the peak in the range of 1 to 10 delta ppm. We know that generally in 1H NMR the peak will be shown in between the 1 to 10 delta ppm, and this is typical the range in the chemistry. What is done to set called is center frequency. That is nothing but the center of the frequency on the offset mode. The offset value basically represent the center of the spectrum. So once the center is set to 5, if we use 1 to 10, so center is set at 5 ppm, you can set the whole spectral width, but you have to do the spectral width. So we can say that it is nothing but to fix the ppm range, that is also known as spectral width. So after that what happens? So after that, if concentration of the solvent is higher, solvent suppression is necessary. Why solvent suppression is necessary? If the solvent concentration is high, the residual peak, I mean undetected peak, is also higher. So it is necessary to suppress that. Otherwise what happens? So with correlation with the solvent residue peak, other peak also minimize, and due to that minimization is a correlation effect. Due to that it minimize, we cannot observe the peak. So to avoid that type of difficulties, solvent suppression is necessary. Solvent suppression is required, then the exit frequency of the solvent line has to be determined, and this is done by first recording an initial spectrum without solvent saturation and determining the extra frequency of the solvent peak. The saturation frequency is then set on the solvent line and the spectrum is acquired again. So this is the things, what is the meaning of that thing. Otherwise what happens? So in next slide we can see that if we not do properly, then which type of difficulty arise in case of recorded of the NMR spectrum. So here we can see that acquiring the 1D spectrum, we can also acquire the correction. Means it is necessary to carry out the correction in pulse width. Correction in a pulse width. Once the solvent suppression has taken place, the next step is calibration the pulse width. Means 90-degree pulse. Why it is necessary? Why? Well, pulse calibration or pulse width calibration is nothing but we apply only the 90 degree. If we apply on 70 degree, then what happens? If we apply on 80 degree, then what happens? So it is important that 90-degree pulse, and that 90-degree pulse is nothing but we can say that it is a calibration like that thing. So what we, so in the 1D spectrum generally we apply at 90 degree. Why? Because we consider the vector on a z-axis, we apply the external magnetic field on x-axis, and when we apply the 90-degree pulse on y-axis, generally the vector will come from the z-axis to xy plane. Z-axis to xy plane. So if it is on z-axis to xy plane, not on x-axis, not on y-axis, only xy plane, means signal will not be determined or detected by the detector. So that's why pulse width correction or calibration is necessary. Let us see that here you can see this red arrow is on a z-axis. This is nothing but the vector. Now we apply the pulses on 90 degree from y-axis. So it will come from y to x-axis. It will come from y to x-axis. So you can see here the arrow on x-axis. So that is the 90 degree. Now further 90 degree if we apply, then it comes to the 180, exactly opposite to the z-axis or natural vector of this. Then further we apply to 90 degrees and it is 270 degrees. If it is 270 degrees, then it is minus y-axis. If it is on minus y-axis, so we can say that is negative. So signal will not be detected. And then further we apply 90 degrees, comes to the original position at on z-axis, that is known as 360 degrees. So if the vector on x-axis, vector on y-axis or vector on opposite to z-axis, then signal will not be detected. So exactly 90 degree pulse, so it comes to the x. If it is on a 80 degrees Celsius or 70 degrees Celsius, then what is the vector will come onto the xy plane, and that cannot be detected by the detector. So that's why 90-degree pulse width is determined and the pulse width and calibration is necessary. 36-degree it means 0, and 0 it is not possible to detect that. So that's why 90-degree pulse calibration is required. Here we can further explain this slide how. So calibrate the 360-degree pulse. A series of 1D spectrum is acquired with the initial guess the pulse width. Okay, the spectrum which is no signal is observed in one where the pulse width has reached to 360 degrees. It is opposite to like that. So here we can increase one by one. So after that it is opposite, means negative signal will be detected, and after that it will at 360 degrees then pulse is and signal will not be detected. So the calibration, the 360-degree pulse, a series of 1D spectrum is acquired with an initial guess of the pulse width. The spectrum is which no signal is observed is the ones where their pulse width has reached to 360. So here you can see that is 3 degrees. Start varying the pulse width from 30 microsecond to 60 microsecond in step 2 microsecond. So if the correct 90-degree pulse with the 12 microsecond, then null will be obtained at 48 degrees. So means here. So the value of 90 degrees then obtained by dividing the value of 360 pulse by 4. So we can do 90 degree, further 90 degree, 180 means opposite to that things, 180, then further 90 means 270, we can get the negative signal. Further we apply 90, so it is 360, there is no signal, and further we can increase by the means next scan will be start. So we can get the peak. So this is known as the pulse width correction or a calibration. It is also a one important thing related to the recording of the NMR spectrum. Now, what is the importance of 90-degree pulse? So 1h90-degree width is one of the most important parameter in NMR experiment, and it is varies with some factors. First one is the temperature, second one is tuning, third one is the composition of the sample, fourth one is the hardware, fifth one is the pulse width, usually does not vary with the shimming and concentration of the sample solution. And if 90-degree pulse width is not calibrated properly, the sensitivity of the spectrum is reduced. So solvent suppression is also affected. So these all factors are affected with the 90-degree pulse. We go one by one. First, that what is the temperature? If temperature is not clearly, then spectrophotometer is not working properly. So it may create some hurdles in the recording of NMR spectrum. Turning means the adjustment of the radio frequency. If it is not properly, then the range we provide for the molecule, it cannot be absorbed if they are not matched with the initial frequency. So it may create some hurdles or mistake in a recorded of NMR spectrum. Third one is composition of sample. Means by increasing the salt concentration, particularly in case of protein, salt concentration, the pulse width tends to be very longer. So it make a broad spectrum or broad peak. And amplifier, or we can say the receiver gain. So if we cannot adjust receiver gain very properly, amplifier is not working properly, pulse width will be longer. So it is further converted on the broad spectrum. Pulse width usually does not vary with the shimming, and concentration of the sample will not be affected to the pulse width. And 90-degree pulse width is not calibrated properly, means we set in a XY plane or a negative plane. At that time signal will not be detected. So it is also necessary. And sometimes if the concentration of solvent is very high, so suppression is also necessary for that thing. So here we go one by one things related to that things, how it can be worked. So in case of this slide, because after setting the pulse width, next step is spectral width. Spectral width we have already discussed, but here we give some important part of that things. Spectral width means set the range of chemical shift. I mean, if we expected the peak in 10 for small molecules in 0 to 10 delta ppm, so we have to adjust that things in 0 to 10 delta ppm. After 10 delta ppm, if any peak is obtained from the sample, then it cannot be detected in that region. So an initial spectrum is acquired with a large spectral width. Means we use 0 to 15 in the spectrum, and the spectrum width is adjusted to the desired value. So it is just like 0 to 15 in delta ppm scale. Spectral width is basically the range of chemical shift where you can accept to receive the peak. So we have to set the typical value as per the constitution of the molecules. If not set properly, many peaks shifting or setting outside of the spectral width, so which cannot be observed when we recorded the spectrum as means here is the some devices which is also known as filter. So filter can cut this spectrum and we cannot observe that things. So not selecting the appropriately spectrum width results of folding or aliasing of a peak. So this peak difficult to distinguish from the unfold peak. So that's why correction in a correction in a spectral width is also necessary, or we can say adjust the spectral width is also necessary for these things. Now in next slide we can discuss about the delay. What do you mean by delay? So we have studied two type of delay. One is for the single pulses, and that is known as preparation delay, which is also designated as T1. Second, after completion of one peak, further we apply the start the new step. So we give some delay for the preparation, that is known as T2. That is known as T2. So what is the importance of T1? What is the importance of T2? So first we think about the T1, relaxation on delay. Next important parameter is relaxation. Relaxation delay is the delay before the first pulse is applied. This is also known as preparation delay. Why it is necessary? To set the equilibrium. To set the equilibrium. So once we insert the sample into the magnet, we give some time for the equilibrium. We give some time the equilibrium. That is known as preparation delay, which is also known as T1. Now what is the value of T1? So delay should be sufficient long for system to reach the equilibrium. The value is for the delay is ideally 5 multiplied by T1. Ideally 5 multiplied by T1. But usually we said it is 1.25 into T1. T1 is the delay. So generally we in terms of 5 like 5, 10, 15 microsecond like that thing. But here generally we use 1.25 into T1. So typically relaxation delay is 1 to 10 seconds. It is 1 to 10 seconds. And T1 usually decrease with the size of molecule. T1 is decreased with the size of molecules. Hence the smaller molecules, T1 is less than 5 seconds. T1 is for the 5 seconds for the small molecules. So remember to bring the magnetization sufficient back to the equilibrium, because when we apply this pulse, the FID is like the signal has come to the XY plane during this period. XY plane during this period, that signal has come away from the Z axis to the XY axis. So after the repetition of this process, signal along with the Z axis is necessary to start the process. Given delay is necessary. So why we give? So in slide, I mean correction in 90-degree pulse, we have already seen that actually signal is on a vector is on a Z axis. When we apply for the 90-degree, if we apply for the 90-degree, it comes to the XY plane. I mean it is on a X axis to Y axis to the negative X axis, and then comes to the Z axis. So after completion of that XY plane, it comes on a XY. Further it reach to the Z axis, vector will reach to the Z axis. Some preparation time is necessary, and that preparation time is known as relaxation delay or preparation delay. So here we setting this acquisition time. What do you mean by the acquisition time? Acquisition time is the duration time for which FID is acquired. This difference for measurement time, which is the total duration of the equipment, means if T2 is very short, T2 means acquired time. If T2 is very short, then signal decay very fast. Signal decay is very fast. If signal decay is very fast, or reverse, if T2 is very short, signal decay is long. So it depends on the acquisition time, depends on the it is directly related to signal decay. If it is very short, T2 is very short, signal decay is fast. T2 is long, signal decay is T2 is short, signal decay is very fast. So it means oscillation is reduce the amplitude because T2 relaxation. Because it T2 relaxation. What is T2 relaxation? T2 relaxation is nothing but after completion of one scan, when we proceed for the second scan, we give some time for the equilibrium. We give some time for the equilibrium. That is known as preparation delay or T2. Acquired time or T2. So T2 it is related to that. Here I have given some calculation related to that. T2 is some point is 0. record the NMR signal depends on T2. Therefore, it is necessary to know what is T1 and what is T2 for recording sample. Intensity of FID I is equal to I0 cos omega. Omega means we can say that it is nothing but the angular frequency, angular momentum. Cos omega T into experimental minus T upon T1 minus T upon T2. So if we put value of this T2, it is 0 to T2. It is 0 to T2. If we put 0, then this value is 1. This value is minus 1. So it is I is equal to I0 cos omega T1. If it is value is I0, value is T2, then it is minus 1 related to that thing. So I0 cos omega T2 experimental is minus 1. So it is minus 36. Minus 36 where omega T2 means 36% amplitude will be reduced. If it is T0, decay is 0, then what happens? So T2 level is 0. If T2 level is 0 means no noise. So practically it is not possible. Practically it is not possible and we cannot detect the signal. So some noise is necessary. So acquisition time depends on T2 of the sample. The longer the T2, the FID can acquire for longer time. This will increase the resolution. Data should not be acquired beyond the 3 multiplied by T2. By this time, the signal has decayed. The data should not be acquired beyond the 3. By this time, the signal has decayed to 0 and only noise is collected. So T2 small molecule is in the range of 10 millisecond to 300, 100 microsecond to 300 millisecond. So that's why T1 and T2 is important. Now we discuss regarding the sensitivity of the NMR spectrum. What is the reason for that? The sensitivity, it can be generally measured in the form of signal to noise ratio. Sensitivity is generally measured in the form of signal to noise ratio. So some factors which are affected to the signal to noise ratio. So first one is the sample concentration. If concentration is higher, signal to noise ratio is higher. I mean to say that it is a linear function of the S by N. Second important point is temperature. If it is inversely proportional to signal to noise ratio. So if temperature is higher, it default distorted the function of the spectrophotometer. As a result, what happens? S by N ratio is higher. So we can say it is inversely proportional. It may be increased, it may be decreased like that. And third important point related to the affected region, that is magnetic field. Strength of magnetic field is also a linear function of signal to noise ratio. Means strength of magnetic field is higher, we can prove the S by N ratio. If it is lower, we can decrease the S by N ratio. And fourth important point, it depends on the types of nuclei being observed. It's a linear function of gyromagnetic ratio. And the measurement time used to record the data means it is related to the acquired time. So S by N is proportional to under root of T. Means acquired data time required for that thing. So these are the some factors. We go one by one. After that, first we think about the setting the receiver gain. Receiver gain means it is a function of amplitude related to that, and it is nothing but the function of hardware. It is nothing but the function of hardware component. To receive the signal, optimization is necessary. So for the optimization means carry out the amplification, and which is known as receiver gain, So it is done by the ADC. ADC means analogous to digital converter. So ADC not only work for the sample signal, but it is also work for the solution signal. So if we amplified the signal of the samples, it is also amplified simultaneously. It is also amplified the sample signals, and as a result, sometimes what happens? It is signal of the solvent merged with the solvent signal. So we cannot find. It is merged with the so we cannot find out that thing. So solvent concentration is high. The signal exceeds the range of ADC means it is also known as we can say the high overflow of the ADC. It is also known as overflow of ADC. So receiver gain adjusts to that signal in the FID with a maximum intensity so that it is maximize the dynamic range of ADC. And the receiver gain can set either manually or automatically. So it depends on the concentration as well as abundance ratio. It is also dependent on, we can prove that by the number of scans. So we can say that it is dependence on what? It depends on the concentration of the sample. So in next slide we continue what how the scan will be effect to the that things. Number of scan is one of the important parameter. Number of scan is one of the important parameter for the resolution or prove the intensity of the sample signals. How it is possible? So once we increase the number of scan, intensity of the signal is increased. Intensity of the signal is increased. We can say it's a linear function of S by N ratio. It is a linear function of S by N ratio. Simultaneously noise level is also increased. Simultaneously noise level is all. So sequence root of the number of scan. Sequence root of the number of scan. If we do that, it depends on the concentration. So it is applied in the form of to the power of 2. The number of scan given to the power of n, where n is equal to 1. So minimum scan we require it is 2. If n is equal to, so we go for the 4 scan. If it is 3, so we go for the 8. So minimum 2 scan is required for the solvent suppression. And means one is blank, one is with sample. So solvent suppression is possible with the help of number of scan. So the minimum 2 scan is required for the solvent suppression. If the sample is highly concentrated for 1H NMR scanning, so 8 to 16 scan is enough for that things. And for C13 it is 128 to 256. It is enough or sufficient for the scanning. Means we can measure the signals or detect the signals related to that things. So we can say that number of scan is also important for that. After that things we can discuss the solvent suppression. Why it is necessary? Already we discussed when we think about the spectral width and pulse width, but here we discuss as a different one. Already previously discussed, no doubt. So we give some important information why it is necessary and what we do. So we already discussed this part. So we give only the important point related to the solvent suppression. That means which is also known as solvent saturation or pre-saturation is necessary. When it will be happen? So before applying the 90-degree pulse, we applying the radio frequency continuously to the sample. We applying the 90-degree pulse to the sample. So at that time solvent molecule is saturated and it will distribute it at a different 2 energy level as per the Boltzmann's distribution law. So population is very same. Means population difference for the solvent is 0, and that is known as pre-saturation. So when we acquire, further we give the 90-degree pulse. At that time solvent cannot be affected. Means redistribution of the solvent molecule will not be takes place, and that's why we suppress the signal of the sample. So that is known as solvent suppression. So if the data is acquired in the deuterium solvent, then solvent line minimize the solvent suppression is not needed. In sophisticated 1D experiments such as DEPT, means to distinguish CH2, CH and CH3 proton, just we apply this DEPT pulse program. DEPT, so at that time solvent suppression can be achieved using the phase cycling. Means we carry out the phase correction, or we go for the noise line correction. So that is known as phase cycling. And the 2 minimum scan is necessary for the solvent suppression. For aqueous solvent pre-saturation or techniques such as it is known as Watergate or WAT can be used for the solvent suppression. So this is related to the solvent suppression. Other things, how saturation will be taken, we already discussed in previously, but just we give the idea related to that things. Now processing of NMR, generally it covers these all points. What is that? So first one is nothing but the applying a window function. Now window function, in another sense we can say that improve the resolution or enhance the resolution. Second one is zero filing data. Zero filing data means correction of the pulse width. Then Fourier transform means acquire the spectrum in the form of signals. That is known as Fourier transform. Then pulse correction means given the T2 times SAT, that is known as spectral width. And then baseline correction means phase correction. But in all cases baseline correction is not necessary, but we see how it is possible and what we do for that. So this picture you can see that it is nothing but the window function of the suitable sample for the simple multiply with the FID. Simple with the multiply with the FID. What it means? We can say that we can increase the number of scan. It will decrease the S means improve the resolution, or it is directly affected the S by N ratio. So we can get the intense peak related to that things, or we can increase the or amplify the signals. So that is known as window function of the suitable from the simple multiply by the FID. The next is in the above experiment, window function is the initial part of FID is given more weightage and the sensitivity S by N is improved. It is nothing but we can say amplified the signals related to that thing. Next, it is nothing but the how the resolution will be enhanced by uh, increasing the FID length. By increasing the FID length, we can increase the resolution. So if T2, it depends on the time, it depends on the value of T1 and T2. If T1 and T2 is more than 1, then we can get the broad peak. If T1 and T2 is less than 1, we can get the intense peak. And that's why this is known as, directly depends on the preparation delay as well as acquired time. So from that, by setting the T1 and T2, we can also increase the resolution enhancement. It directly depends on the length of FID. So here you can see the length of FID is high. You can say the length of FID is very low. Here it is the exact FID. So you can get the intense peak. So this depends on the length of FID, and it is also related to the T1 and T2. I mean preparation delay as well as the acquired time. So window function is also used as a dealing with the function artifacts. Window function is also related to, so here you can see that all wiggles are same, and once point it is 0, you can get the sharp peak. To avoid the sign wiggles, FID is multiplied by a window function so that the last point goes to the 0. So if we carry out the multiplication, and after that it will be convert into 0. So if it convert into 0, you can get the signal. You can get the signal. So that is known as the window or waiting function. Now we start the second part of this lecture, and that is nothing but the application of NMR small molecules. So generally what happens, we measure the chemical shift value, determine the chemical shift value, show the splitting pattern of the signals and number of the signals. These are the general things in case of the NMR spectroscopy we observed, and from that we can evaluate the structure, interpret the spectrum and evaluate the structure. But here I am not discussing the routine application of the NMR spectrum. I am discussing relating the regioselectivity, stereoselectivity and desmotropy, how the NMR spectra will be help us. So you can see here I have taken as a practical condition or as experimental, I have taken the one molecule, and that is nothing but the purine molecules. That is nothing but the purine molecules. But actually what happens, I have taken the purine molecules. That purine molecule possesses 2 chlorine atom at position 2 and 6. Now this purine molecules treat with the amino compound. It may be alkyl aliphatic amine, or it may be aminoquinolide derivative. So when we do that, the question is that where the reaction will be takes place, and that can be represented in the form of regioselectivity. That can be represented in the form of regioselectivity, whether the Cl replaced by this amino group at second position or it is sixth position. So it is formed like that one thing. It is formed like that one thing, it is formed like that second thing. So which one is the correct structure where the reaction will be takes place? So by studying the NMR spectrum, different method, and we can prove that it will be takes place at sixth position. So we can say the regioselectivity means properly where the reaction will be takes place on the replacement will be takes place. So we seen here. Here you can see that before go for the 2D NMR techniques or the second pulses, it is necessary to know about the single pulses. If we have a knowledge of the single pulse, it helps us to interpret the secondary 2D NMR techniques. So here we have recorded the 1H NMR spectrum of this purine aminoquinolide derivatives, and we also report here the C13 NMR spectrum of the aminoquinolide derivative. And here you can see the chemical shift value related to proton as well as the chemical shift value of the carbon 13. But why we do that? So in the next slide you can get the idea which technique we have used for the interpretation of this compound. So here for study the regioselectivity of this particular reaction, we use the heteronuclear multiple bond coherence spectroscopy, and it is what? So we can say it is over a 2 or 4 bond usually between the proton and carbon nucleus. Means heteronuclear correlation will be takes place between proton and neutron. So interesting. HSQC and HMQC some limit. What is HSQC? Means single quantum coherence spectroscopy, and HSQC means heteronuclear multi-quantum coherence spectroscopy. Limit is that when it cannot be detected the 1J. It is coupling correlation due to the J coupling are detected in the limit to the near range in the this tech means 1J it cannot be detected. So that's why we not use HSQC and HMQC, but instead of that we use HMBC. HMBC is extending the detection limit to the long range J coupling and suppress the signal bond with J coupling. What is that? So this is known as 1J coupling. This H correlate with this carbon, then it is known as 1J coupling. Now this H correlate with this carbon means it is one hydrogen to carbon, one bond, carbon to carbon, second bond. So that is known as heterocoupling, means this H correlate with this carbon. H is correlate or interact with this carbon. So that's why it is known as 2J coupling. If it is correlate with this carbon, then 1, 2 and 3 means beyond 3 bonds. So that's why it is known as 3J coupling. Same thing it is possible here. So this is the one, then second. So it is also a 2J coupling. Now when we study the HMBC of this particular compound, what we get? So here on x-axis we have take proton NMRs. Here we take in one x-axis we take the proton. So it's not a single pulse frequency. It's a we use two pulses. That's why it is known as 2D NMR. We use the two pulse frequencies means two pulses. So that's why it is known as 2D NMR. So in x-axis we recorded this one pulse and on y-axis we recorded the second pulse. So now in one pulse we recorded here proton NMR spectra and in y-axis we recorded second pulse we recorded here 13C. Now we focus on the NH peak. We focus on a H attached with the nitrogen NH peak. So this NH will be here. Now this NH, when we travel from x-axis to down to the gravitational force, so we find out the 4 different peaks. That is coherence peak. That is known as coherence. So it means that this proton has a correlation with 4 different carbon atoms. This proton has a correlation with a 4 different carbon atoms. So when we determine this coherence peak, first one, and we travel towards the y-axis, so we find out these peaks of the carbon that is related to carbon number 5. That is related to the carbon number 5 means this junction point of this purine ring system. Then further we travel second carbon in covalence peak. So when we find out that it is related to the carbon 12. So it is situated in the phenolene ring system. Then we go for the third peak. We find out that C17. So it is related to the further it is situated in phenolene ring system, and last one we find out that it's C6 which is related to the purine ring system. Now this find out this means it is either 2J coupling or 3J coupling. So this H proton of NH correlation with the C12 means it is 2J coupling. We find out the 17 coherence ping, so it is due to the 3J coupling. We find out here the 5, so it is also related to the 2J coupling. We find out the 6 number, so it is related to the 2J coupling. So we find out the whole relation with this. It means when we find out the correlation with the C12, C13, it is okay. But when we find out the relation with C6 and C5, it is only possible when the replacement of this chlorine takes place at which is situated at carbon number 6. If it is replaced by the carbon number 2, it means relation we cannot find out with the carbon number 5. So that's why we prove that things. Now next important point, it is related to find out the tautomerism. In case of purine molecule C9 and C7H proton transfer will be takes place very easily. So here we studied by using the nuclear over-Hauser effect. So here we reported 1S1H spectrum. We reported 1H1H spectrum, and from that we find out that this is the diagonal line and this is the off diagonal. So when we study regarding the diagonal line, we complete this peak. So find out that this H is situated at position 7, not at position 5. So that type of study we can do with the help of 2D NMR spectrum. So it is uncertain that the reaction of 3-aminophenolate and aliphatic amines were taking place at C6 position of the purine molecules. Tautomerism in purine between C7 and C9 position is also confirmed by NOE experiments, which is not limited up to the tautomerism but also useful for the substitution confirmation at C6 rather than C2. Next, we have studied the exact dihedral angle between these molecules. So here we carry out the study of natural compound, that is nothing but the hesperidine. Hesperidine generally it is present in the orange fruit pulp. So this structure you can say that hesperidine possesses two pyranose ring system as a substitution of the flavonol ring system, and also possesses one aromatic substitution at flavonol ring system at second position. So we find out the dihedral angle between these two aromatic ring system. No doubt we can find out all over the information related to the whole molecules, whether it is axial or equatorial, but we also only concentrate on the dihedral angle. And we know that what is the dihedral angle. Before we proceed for the dihedral angle, just I give some information related to hesperidine. Is a flavonoid molecules found in the citrus fruit, especially difficult to extract, classify and characterize. So we carried out the study of dihedral angle, coupling constant and different NMR techniques. So what is the relation between the coupling constant and dihedral angles? It is already proved by the Karplus equation and its modification. So by using that Karplus equation and its modification, we find out the value of dihedral angle using the Maslow version 1 software to find out the exact structure of that things. So result data said the calculate the dihedral angle can prove significant method to assign the virtual configuration of natural products and also resolve the stereochemistry of hesperidine. So for that we carry out the 2D NMR technique. We use the different 1D and 2D NMR technique. So what we do? So first this slide will show the how to isolate the hesperidine from the citrus fruit. So we take the bark of the things, then make it fine powder, carry out the soaplet extraction method with petroleum ether, and then further proceed for the methanol, then treat with the 6% acetic acid, we can get the hesperidine. Now this hesperidine we carry out the study. For that we scan the compound for 1H NMR as well as 13C NMR, and same instrument we use 400 megahertz. Then we carry out also study the NOE study, HSQC and HMBC 2D NMR technique for that things, and broadband observed it is 5 mm. So we require only the, for C13 we use the 100 megahertz frequency, and for 1S we require 400 megahertz. So we set this frequency and we carry out the study. So in this slide we reported here the two techniques. One is 1D NMR proton spectrum, 1D NMR proton spectrum of hesperidine. In second, we take simple Koji spectrum, 1S Koji spectrum. But you can see that what is the noise level, and due to this noise level, it is difficult to interpret the 2D also. It is also difficult to D also. So what we do? To suppress the noise level, we use the NOE technique, and we can get the sharp peak. We can get the sharp peak. We also carried out, record the C13 spectrum. Now what we do? We correlate with the NOE heteronuclear NOE spectrum, means find out the relation between carbon and hydrogen, and from that coupling we find out the heterocoupling, means coupling interaction between hydrogen and water. Now this value we put in that equation. This value we put on this equation by using ABC parameter and derive the data set more than 300 times. So from that we use this thing. Now this value we apply in this software. This value we apply in this software. So we find out the relation between C1 and C2. What is the dihedral angle in C1H and C2H? So exactly what is the value? So in next slide we can see that for C3 and C2, 3J coupling it is 2.92, and the dihedral angle it is 51.8, means it is equatorial in position. For C3 and C2 it is 12.08, and we find out the dihedral angle it is 179.9, means it is axial. So exactly we find out the dihedral angle related to that things. So next we can say that C3 C2 2.92, so value is 51.8, it is equatorial position. It is equatorial position. So C3 and C2 are equatorial position. C3 and C2 at axial position, then it is 170. So this 2H, out of this 2H, one is equatorial, one is axial position, means these two are axial or equatorial. So here is H, one side is H, one side is aromatic ring system, and second side is here, it is also H and aromatic ring system. So from that generally we find out that aromatic ring as a bulky group it is at equatorial position, and 3H is also a equatorial position. So we find out this relation in the hesperidine concern. So computational dihedral angle with the help of MESH RG version 1.1 from the coupling constant to determine the relative configuration as well as identify the unpredicated substituted routinous proton of naturally occurring hesperidine. So we use this software, we use this pulse programming for any natural compound to find out the dihedral angle and exact what is the situation in 3D structure. So we can use this technique for that things. Now another important application, that is Desmotropist. It's a new approach. Desmotropy is a new approach, but actually we can say it is one type of prototopic shifting. It is nothing but the one type of prototopic shifting. So we can see here how it is helpful for us. Desmotropy is a prototopic tautomerism phenomena and generally challenging to be distinguished by analytical technique. This phenomenon was first introduced by organic chemist Jacobson in 1988. Uncertainty about the concept between polymorphism, tautomeric polymorphism, and desmotropy. So what is desmotropy? Desmotropy is one type of desmotropy. If we involve the proton, then we can say it is desmotropic technique. So development of proton transfer was carried out by using the different solvent polarity to generate two distinguished destrosons. So we carried out this desmotrope by using protic solvent as well as aprotic solvent. Means this H will be transferred to this third position and fourth position. So these two are the desmotrope, or these two are the desmotrope, means prototopic shift related to that thing. So polar protic solvents having a labile acidic H plus proton attached with oxygen or nitrogen can generate the hydrogen bonding with the solute. And due to this high polarity of the solvent, it will stop hopping to annular proton transferred in the tetrazole ring system. So in next case, we use the protic solvent, we use the aprotic solvent, and we develop these two molecules, form A and form B. Form A means it is 22 and form B it is 23 in all over structure of this alpha atom. So in case of that things, we record the solid state NMR and solution state NMR and solid state NMR. But here we use N15. We use N15 NMR, not 1H NMR, not 13C NMR, but we use N15 NMR. So relation with hydrogen with nitrogen we can find out. So this is the N15 of form A. So you find out 1, 2, 3, 4 related to that. So N5 can be observed. It's from imidazole ring system. N5 and N2 there is no change in form A and form B. Why? Because desmotropy occurs in tetrazole ring system, not into the imidazole ring system. So there is no change in that ring. But in form A, 22 is not observed. Form A, 22 is not observed. Why? Because we record N15. We record N15. So as polarization is very high as compared to the N15. That's why this N22 is not reported, because it is attached with the hydrogen and it will use for the hydrogen bond formation with the protic solvent. So that's why 22 is not observed. 23, 24 and 25 it is observed. But in case of B, when we carry out the solid state NMR, so N5 and N2 no change because it is imidazole. N22 is observed. 23 and 24 is not observed. Why? Because this H may be 23, this H may be 24. It is identical. It is nothing but the identical. So that's why N23 and 24 is not observed, and N25 it is as it is in a form A. So from that prediction, here you can see form B. Now in case of form B, you can get only the 2 peaks. You can get only the 2 peaks. It is one related to N2 and N5, N2 and N5, and it is related to the N25. Remaining 2 are not observed. So this is the reason why. What is the thing? So from that we can conclude that how it will be helpful. The development of new aspect to study the desmotropy is effective for the confirmation of A and B at tetrazole ring system. You can use any tetrazole ring system or any ring as per the tetrazole, means transformation of hydrogen from as a proton from one position to second position. You can carry out the desmotropy study in presence of by developing the crystal. Different polymers, you can do that. No doubt we can do that things with the help of X-ray crystallography also, but this is easy as compared to the X-ray crystallography texture, because the big molecule crystal development is not very easy, and that's why we use the desmotropic studies carried out with the help of 1H Nmr spectroscopy. And last, thank you for listening me for a 1 hour lectures, and I will further if you have any question you can put me on a chat so I can do that things. Once again, thank you.